some forces on this diagram. So first of all, the forces on A, it's going to experience its weight, which we're told the mass is m, so the weight is going to be mg. Now there's a force that's stopping the particle just moving into the ground, and that's the normal reaction force, and it's normal to the surface, so it's an angle here. So call this R. I could call it RA, but there's no normal reaction force on B because it's suspended by this rope, so it's okay to do that. I'm also going to put on this angle here, which is going to be 30 degrees. Okay, and you can make an argument for that by drawing a right angle triangle. This is 90. This here will be therefore 60, and therefore that one's 30 because this is also a right angle. But you just want to get into that habit of knowing straight away that's going to be 30. And then there's going to be a tension force acting from the string up the slope. So I've got T. Okay, we are also told that it's a rough plane, but at the moment I've not looked at, well, actually, sorry, I will jump to this. It says, given that A is on the point of moving down the plane, then that means the friction is going to be opposing motion and also acting up the plane. So it's going to be a frictional force going this direction, which I will call F with a subscript of capital R. So those are all the forces acting on A. Now let's take a look at the forces acting on B. It got a weight, which in this case is mu m times g, and then a tension acting up, stopping it or trying to prevent it from just falling under gravity. So those are all my forces on the system. The only thing I've not added is that there's a coefficient of friction, mu. So I'll just put that up here. Now, as I mentioned, we're told that A is on the point of moving down the plane, which is why friction is acting up the plane. And then we're asked to find the exact value of mu, the coefficient of friction, when lambda is a quarter. Now, this is a connected particle system, so we can look at A and B separately. In fact, we have to. We can't look at them together because they're not accelerating in the same direction. So first of all, I'm going to look at A, and I'm going to resolve forces perpendicular to the plane. Then R, which is going away from the plane that way, the only other force acting perpendicular to the plane is the weight. So R is going to equal mg cos 30. That's good to know. Now, the frictional force is always less than or equal to mu r, but in this case, because it's about to move, it's actually equal to mu r. So it's going to equal cos 30 is root 3 over 2. So it's going to equal root 3 over 2 times mu mg. Now I'm going to resolve down the plane, still on A, because it says it's about to move down the plane. It doesn't really matter. So I'm going to get mg sine 30. Then it's going to be equal to fr plus t. So that means, oh, sine 30 is a half, by the way. So a half mg is going to equal root 3 over 2 mu mg plus t. Okay, what I've not yet done is look at B. So that seems the obvious thing now. So I can get another relationship between T and the mass. So for this, I'm going to resolve up, and then T is going to equal mu mg. Now I can put the two together. So therefore, a half mg, and I will at this point also say that it's a quarter, I suppose. I said I was going to work in terms of mu, but it just makes sense to substitute it in, I think. So a half mg is equal to root 3 over 2 mu mg plus a quarter mg. Now I can just divide through by mg, and then I'm going to get that root 3 over 2 mu. I can minus a quarter, so it's going to equal a quarter, which means mu is going to equal, I can times through by 2 to get a half. It's going to equal 1 over 2 root 3, which I could leave it like that, but maybe I rationalize the denominator times top and bottom by root 3 to give root 3 over 6. So either of those two are okay, but this is arguably slightly neater. And remember, we've asked for the exact value, so that is how I'm going to leave it. Nice. So I hope that makes sense. I've put the forces on. I've just carefully maneuvered through applying forces to A in two different directions to create these relationships. Use the frictional force, then use the forces on B to get the tension force, bring it all together and solve to find mu. On to 1 part B, we're asked to show that the value of lambda must be less than a half. I'm going to talk about this in two different ways. First of all, coming back to resolving down the plane, we must have that this mg sine theta, which becomes a half mg, minus t, because I'm sort of applying f equals ma down the plane, that must be greater than 0, since it's about to move down the plane. Now t from above is lambda mg before we put the quarter in. So we can divide through by mg. Maybe I should just show a few more steps. So a quarter mg minus lambda mg is therefore greater than 0. Now divide through by mg, so we can see that lambda is less than a half. Now, an alternative, this is actually how I did it, and I think it's valid, but I'm putting it secondary, just in case there's something I've missed, is we can return to this formula here. So we've got that a half is going to equal root 3 over 2 times mu plus, now that quarter was lambda, so plus lambda. And therefore lambda is going to equal a half minus root 3 over 2 mu. So since lambda is greater than 0, because we're told it's a rough surface, then lambda is going to be less than a half, because I'm subtracting something that is positive away from a half. So we get the result that way as well, I think. On to part 2, we've got a new version of the system to look at. Lambda has changed from a quarter to 2, and the system is now accelerating, and we're asked to find the exact value of mu. Let's get another diagram down, carefully drawn. So, some modifications needed. This lambda is now equal to 2. And what that means is that it's heavier. B is heavier than A, and it's actually going to accelerate down. And A is going to accelerate up the slope rather than down the slope. This has a big impact because the frictional force always opposes motion. It's now going to be going down the slope. So I'm going to look at B to start with. And I'm going to, because actually B is a little bit easier to deal with. I probably should have done that the first time round, like deal with the most simple things first. Let's apply F equals ma down the slope. So 2mg minus t is going to equal ma. Now we're told that a is equal to g. So it's going to be 2m times a quarter This means that t is going to be 2 mg minus a half mg, which gives 3 over 2 mg. On to A. Now the normal reaction force is still going to be mg cos 30, and therefore the frictional force is still going to be mu times that. It's going to be root 3 over 2 mu mg as before. What's different now is the motion. So let's apply F equals ma up the slope. So T minus mg sine 30 minus Fr is going to equal ma. So it's going to be a quarter mg. Substitute in for T, 3 over 2 mg minus a half mg minus root 3 over 2 lambda mg is equal to a quarter mg. The mg's can just cancel out, and 3 over 2 minus a half is just going to be 1. So I've got 1 minus root 3 over 2 mu is equal to a quarter. And I can rearrange that. So I could multiply through, but in this case, actually, I think it's going to be easier not to. Root 3 over 2 mu is then going to be 1 minus a quarter. That's going to be 3 quarters. So root 3 mu is going to be 3 over 2. Mu is going to be 3 over 2 root 3. This answer's pretty good. We can do a little bit better though. We can actually multiply through by root 3, top and bottom. Okay, rationalizing the denominator essentially, so that becomes 2 times 3. The 3's cancel, which gives us a final answer. Mu equals root 3 over 2. It's got to be said, there's a lot of places that you can make mistakes in that, but it's a really nice end to this mechanics paper. Good question.